following series, this series here, is an arithmetic series. And in the previous video, we described how we can get each of these terms here. And we used basically a description of how to get what are called partial sums, since this is an infinite series and we can't add up everything to infinity. So what we said was we can work out what s sub 1, s sub 2, s sub 3, s sub 4, and s sub 5 are just by plugging in values of n. And basically what we notice here is that the values of s that we have don't approach a particular number. It just keeps growing. So s sub infinity is just going to be a huge number compared to s sub 1. So what that means is that this particular set of partial sums does not converge, which means that our series does not converge. And all we're looking for here is, do our partial sums get very close to a certain number? In this case, this thing just keeps getting larger and larger, and it does not converge. So what we notice here is our partial sums kept getting larger and larger when we're dealing with this arithmetic series here. So what we can say for all arithmetic series is, because of how everything is set up, all arithmetic series will not converge. But what about this geometric series over here? Does it converge or not? And by the way, we can tell it's a geometric series because there's only multiplication here. So now let's talk about getting the partial sums of the series. If we substituted n, we'd end up with s sub 1, s sub 2, all the way through s sub 5 if we needed, and we can keep going if we wanted to. Just like in the previous example, these numbers are just going to get huge. And so there is no number that this is basically going to get close to. So what we can say is that this series, because it doesn't really approach anything, because it's going to keep growing unchecked, that it will not converge. So because the sequence of partial sums of this particular series here gets larger and larger, it gets up to be a huge number, we're going to again say that this series does not converge. But what about this one here down at the bottom? What about this geometric series, infinite geometric series that we have at the bottom here? Well, there's a difference between the two. This one has 2/3 right here, that one has 4. So the common ratio is different in these particular series. It turns out that as long as that common ratio is less than 1, that the series will converge. So this series, remember, this series has 2/3 as its common ratio. So what that means is that this series, according to what we just said, does converge, and we'll see exactly why we say that this particular series converges in a minute. So we need to figure out what this series actually converges to. So what number do the partial sums get very close to if we get out, say, to 1,000, or if we get out to a million, the millionth partial sum? What would that be? So I know I wrote s sub n here, but let's go ahead and actually put s sub infinity, since everything goes out to infinity. So the formula that we know that we're going to have to use here is going to be a sub 1 over 1 minus r. And this is going to tell us what happens when this series here, when the n gets very, very close to a huge number. So s sub infinity is going to equal, now we need to substitute 1 as our n value so we can get a sub 1. So a sub 1 equals 3 times 2/3, and we're going to replace the n with 1. So 1 minus 1. 1 minus 1 is 0. 2/3 to the 0 is 1. And then when we multiply it, 3 times 1 is just 3. So all that works out to just be 3. So a sub 1 is 3. So now we're going to take our r value, and that's 1 minus the r value, which we know is 2/3. And if we work this out, we're going to get 3, still in the numerator, and then 1 minus 2/3, that's just 1/3. And when you divide, a fraction is basically multiplying. So this is basically the same as saying 3 times 3, and that's 9. And we can confirm this by looking at the partial sums. So based on what we just said, will this series here converge? Yeah, you can pause the video and try this yourself if you'd like. Okay, so first of all, we'll notice that this is a geometric series because we have only multiplication here between these two terms. There's no addition. Even though we have subtraction in the power, this is just multiplication. So look at the R value. The R value, the common ratio value, is 3. So from what we said, we know that a series is going to converge if the R value is less than 1. And technically, it should be the absolute value of the R value is less than 1. So 3 or negative 3 would be the same problem in terms of convergence. In this case, it's 3 for the common ratio. And because 3 is greater than 1, then we're going to say the following. So the common ratio is 3. So that means that because it's greater than 1, this series does not converge. A geometric series only converges if the R value is less than 1. So let's try this one here. Pause it and try and see if you can work this out. So we know that this is geometric because it's only multiplication here. And we know that the R value is 1/2. So if the R value is 1/2, remember, as long as this number is less than 1, that we know that this series will converge. But what does it converge to? So we had that formula that we had before, which says S sub n equals a sub 1 over 1 minus r. And even though I wrote S sub n here, technically it should be S sub infinity. But anyway, a sub 1 is the first term. And if we plug in 1 for the n value, we'd end up with 5. You can check that yourself. And then if we put 1 here, and the common ratio in this case is 1/2, if we work this out, it's 1 minus 1/2 in the denominator. The 5 is still there, and 1 minus 1/2 is 1/2. When we divide by 1/2, it's the same as multiplying by 2, so our answer is 10, and you can check this yourself.